we're gonna talk about extension of cut matching game. Like, so we finished the analysis of cut matching game, but so that's gonna be useful. That's gonna be, it's a version that people know. Like, it has been around for 20 years, but this new version is a version that I don't think it's taught anywhere, and but you're gonna learn it because it's useful for fast algorithm. Yeah. Okay. Let's see. Okay. So there's two extensions of cut matching game that we learned today. The one with deletion, and the one with deletion and transferring vectors. I tell you what these are, but yeah. This is going to be useful for expanded decomposition, and this version is needed for expanding by line separator. Okay. So let's look at the game with deletion, the first extension. Okay. So here we have two players still, a cut player and a matching player, but here like the matching player can match and delete. So let's see what will happen in this game. Okay. So it's just like cut matching game. You start with empty graph, okay? And then now there is going to be some set that we call active set, the thing that is not deleted yet. Okay. So you start active, which is like the set of active vertices just start to be everything, every vertices. And then for each round, the same thing happens for cut player. The cut player just choose like two disjoint set, AI and BI. But now you're gonna choose something only from active vertices. Okay. And AI is less than BI. Okay. Now, what the matching player would do, first he will choose some set from AI to delete. And then the part of AI that is not deleted will be matched to BI. Okay, so let's draw something. You start with a graph. You have a graph. Okay. Have a graph, then you have AI, BI, that's bigger. And then, okay, actually let's say that this thing is active right now. Only this thing is active. And then we're gonna choose AI and BI. Okay. And the matching player will first choose DI, and this will be deleted. It will be deleted from the active set. So, okay. And the matching player will also choose a matching from the rest of A to some node in BI. So this is what matching player do. Delete something, and the rest that is not deleted, match. Yeah.
When you say delete, do you mean delete from the graph completely, or like
delete from active set?
So they can be chosen again later on, or?
They will not actually. Like once you leave the active set, you leave it forever for this version. Mm-hmm. Yeah. The next version, when you transfer vectors, you can come back. Yeah, but yeah, this one, okay. So in this round, choose AI and BI in the green set, the active set, and then that's what the cut player do. And then the matching player deletes something and match the rest. Okay. And again, you just add the matching to the graph, and the thing that you delete, remove it from active set. All right. So if the deletion is empty, then it's just the same game. Okay. Good. And what's the goal now? The goal is that your active set is expanding at the end. The all one on like the indicator of the active set is expanding. Not the whole vertex set anymore. Okay. Okay. Any question about the game? All right. Okay. So now the claim is just that we can solve this version too. So even when the matching player can delete vertices from the active set, basically we have the same guarantee that there is a cut player, the cut strategy for cut player such that we can choose AI and BI from the active set in time something like NI, the same running time. Now, I also promise that AI is gonna be quite small. It's gonna have size at most this one. And BI is gonna be still big, like more than half of the active set. So even when AI is not too big, we're gonna still say that after a few rounds, indicator of active set is expanding. Yeah. Okay.
So just to clarify on the last part, you said we're only looking at the active vertices for expansion, but we still consider like if the edges that go from like active vertices to inactive vertices still?
Yeah, that's fine. Yeah. So the expansion of the active set just means you can route flow between active set, but the flow can use the non-active part. Yeah, exactly. Okay, so so you see that when you want AI to be not too large, that puts more constraint to it, right? Like normally you want the set to be as large as you can so that you match many things. But here, okay, I said that it's not too large. Why is this? Why do we want this? We use this in next class next week. Okay. Good. So now here's the plan. The plan is the same plan. Okay. How to prove this? Well, we will look at the potential function where you define the potential function to be the sum of the distance of each node, like distance from each node A to the average. What is this average? This is like kind of the point. This is the position of each node A, summing over all active guy and average it. Okay. So this average used to be all one vector, right? Like if this is like a V and this is V, then this is just all 1 over n. But now it's just the average of the active set, the average position of the active set. Okay. Do you recall what PI is? I will not. Yeah.
It's kind of the matrix where each entry like PI UV would be the probability that we go into node V starting from node U.
Yeah, the probability that you go from node, like
From the
PI
first node,
UV
yeah.
is when you start from U and you end at V after I steps, and is with respect to one particular way to walk, which is
The Robin.
the round robin walk. Yeah. Okay. Good. Okay. So this is similar to what we have before, and we're gonna say the same thing essentially that if this potential is close to 0, then we are done. Then the active set is slow expanding. Okay. So let's prove quickly again why this is the case. Okay, so maybe I do it on the whole on the board. Yeah. Okay. So this is going to be similar to the proof that we did this week. So I hope that this is a kind of some extension, but still kind of reminder so that you remember. Okay, so you have this thing, right, which is kind of a sum of now A in the active set, a position of A, yeah, to an average. Okay, good. That's, yeah, okay. So now I can write this as this thing too, AB in active set, and this is just gonna be, maybe call it UA, PIUA minus, this is a vector, so I just take the U's entry of this vector. Okay, good. And this thing, we know that this thing is less than 16. So it means that for each individual term, this is less. So this means that for all, okay. It just means that for all U and A, U and A minus this thing, right, is less than 4n. Just take the square root. Okay. U and A. Yeah. Okay. So now we're gonna get to this one. Yeah. So which says that, so basically, yeah. Yeah. UA minus, this is just triangle inequalities. The distance from this to this, like, yeah. So it's at most this thing. Maybe, yeah, this is just here. Distance from, it's like, if, maybe it's just this thing. Like, if you have x and y, this is at most x minus z plus x z minus y for all y, for all z, right? So I just put this thing here. And each of this is less than 1/4. So this is like, so it means that the probability from U to A and the probability from U to B is basically the same for every A and B in the active set. Okay. So in picture, maybe you can say that like, if this is the whole graph, this is active. Okay. Then if you like look at like the probability that you kind of go from U to, this is U and this is A, this is U and B. Okay. Like the probability that from U you can reach A and from U you reach B, this probability are basically the same. Okay. Like this thing is less than 1. This thing is less than this. Okay. Okay. So, and you can think of, so now let's think of this as a distribution and like, so if you think of this as and the position of, you think of this position of A and position of B as a distribution or as a vector, this just say that coordinate wise they are almost the same. For every coordinate u, they are almost the same up to this additive deviation. Yeah.
And that would be because that's for any A and B, right? That we've proposed.
Yeah, for all A and B, that is active. These things are like, this vector looks like the same.
Up until the 1/2n, right?
Yeah, yeah. For every entry, they deviate by 1/2n. You get this now, right? Like right now, what we have so far is just that, what we can conclude so far is that for every point in the active set, like for every node in the active set, its position now are basically the same. Okay? Okay. But what I want to conclude is even further. So I want to look at this thing. Yeah, wait, what? Okay. Yeah. So I want to look at this quantity, and I want to say that this quantity is big. Okay. What is this? When I sum over all nodes U, and I take mean between these two things, I want to say this is big. Big as in some constant. Okay. So why is that? At least if you don't, like, this is just some algebra, but the way I think about it is this. I think of position of A as some distribution, right? Like this is like a distribution over node 1 up to Vn, and it's like some distribution. Where like this summing over all nodes here is just 1. Okay? And for position of B, this is almost the same. So like they can deviate by like, okay? They can like coordinate wise they deviate by at most something small. Okay. So, and what I want to compute here is just coordinate wise, you take minimum. So you look at the thing in the, that is below both line, both curve. And if they are like, if you know that the area below the blue curve is 1, then the area below the red curve is also 1, and they are all basically the same curve. So when you, even after you take the minimum coordinate wise, that's going to be still quite big. That's really intuitive, and you can just prove it from here if you want to follow algebra. But the mental picture is clear. Okay. So this thing is big. Why this is useful? Okay. So this is useful because of the following. Imagine that I want to send flow from A to B. Okay. Suppose that I want to send flow from A to B. Okay. And I want to send flow from A to B of something like 1/4, 3/4 unit of flow. Okay. So one way to do this is I'm just gonna send from A to U and from U to B. And by how much I gonna do? I just gonna send like, so I know that like I could send from, like there is a way to send flow from U to A with congestion 1 by this much. Like you can send this unit of flow to A by this much. And you can send this unit of flow to B with congestion 1 again by this much. So but this is undirected graph, so if I want to send flow from A to B, I can just reverse the flow here and go here. By how much? Just take the minimum of this guy. The condition is going to be just still 1. Okay. And I can do this from A to B for every node U. And for each node U, I send this minimum of these 2. Then in total, if I do this for every node U, it's just I can send this much flow from A to B, which is still big, like close to 1, and with congestion 1. Yeah.
Can you explain how we go from the first sum to the second?
This one,
Yeah.
From this to this? Okay. Yeah, this is like, this is just because, okay, this is something that like I'm not super, think is so important. Like once you get this picture, you're gonna just be convinced that this is gonna be big, but I can still explain this. So the reason is just, if suppose that you have 2 numbers, right? 2 number, let's say X and Y, okay. And you don't wanna take min, like this is, min is X, right? So what you can do is maybe you can draw like okay. So this thing is the difference.
Yeah.
Okay. This is y minus x. Okay. And then if I just say that I just add this thing and this thing, and then subtract what? How do I do this? Let's see. Good. Good. When I add x and y, and I subtract this thing, this part is 2x.
You get like 2x, so 2 minimums. So,
Yeah.
Okay, makes sense.
2 of the minimum, and when you when you halve it, then it's just a minimum. Yeah. But again, this is something that is like, it's just algebra. Like this picture is the thing that's important. Yeah. Okay. So what I want you to be convinced now is just that, suppose we want to route 3/4 unit of flow from A to B, we can do it with congestion 1. Because of what I just explained. Yeah. Okay. Actually, no. Like congestion is 2. Yeah. Because if A gonna send from A to every U, that's take congestion 1. And from all the U to B, that's another congestion 1. So that's congestion 2. Okay? All right, good. And now, good. So with this, like, I want to claim now that like you can route any demand that respect indicator of active set with congestion 2 or close to 2. So why is that? So suppose that you have this graph, okay, and then you have this active set. You have an active set. Okay, you just saw that we can send, if you have A1 and B1, you can send like a 1/4 from A1 to B1 with congestion 2. Okay. Just by routing from A to everyone and from everyone to B1. But if I want to route from A2 to B2 as well, at the same time, I can do it too. Because like I can just route from A2 to everyone and from everyone to B2. Right? Why? Like because the way that you want to route, like if you want to route from A1 to everyone here with like at most like with this unit. And if you want to simultaneously route from A2 to everyone with this is 1 and this is UA2, you can route simultaneously with congestion 1 here, right? Because you know that you can route the whole matrix PI with congestion 1. So here I just want to, like I just do it for A1 and A2. Okay, so how to route both of these simultaneously? Just route from A1 to everyone and A2 to everyone. That takes congestion 1. And then everyone to B1 and B2. That takes another congestion 1. And it's not just 2 pairs. You can take any meshing and then you can route that. Okay, so the claim is that if you have any demand that looks like a meshing within the active set, you can route that with congestion. If each of this is like if you want to route 3/4 for each of this, you can route with congestion 2. Congestion 2. If you want to route each of this by 1, what's the congestion now? Like not just 3/4, but you want to route 1. What's the congestion now? 8/3. Yeah. Just multiply this by 4/3. Why? Because just whatever you route here, just scale it up by 4/3. Okay, make sense? Yeah. Okay. And now, if you can route, this is like a meshing demand. Okay. Now you can route any meshing demand in. So here's the claim: if can route any matching demand between Ti with congestion something kappa, then you can route any one like indicator of Ti respecting demand with congestion kappa 2. Okay. Why is this the case? Well, you have seen something like this before, but not quite. You have seen that if you can route a product demand, then you can then any respective demand. If you can route product demand with congestion kappa, then you can route any any demand that respect that node weighting with congestion 2 kappa. I can kind of show you that. But this is strong. Like actually, you can prove something stronger. You don't need to lose factor of 2. Why? Because actually, if I take any, let's say, respective demand, D. Okay. So why is that? The fact is that if you have demand D that respect this, you can write it as the convex combination of matching. So this is like a convex combination of matching. Like this is like a where the sum of this thing is 1. It's at least 0. This is not too important, but yeah, like any. So yeah, try to convince yourself this. Yeah, like you can look it up too. Basically, okay, the fact that you wanna you say is this. If you wanna look it up, you say that for all doubly stochastic matrix is a convex combination of permutation matrices. And permutation matrices is just like you can think of it as a matching. So yeah, you can kind of look this up and then convince yourself that if this is true, then this is true. Okay. So what does it mean so far? It means that for any indicator, like any demand that respect the indicator of active set, you can route with congestion 8/3. Okay. So we get this thing. Okay. So now let's try to prove that you can get the bound to you can reduce the potential. Well, the algorithm is gonna be similar. Basically the same thing. Like the cut strategy, just choose random vector, and then project all the points to a random direction. And previously we just look at this line and take the median. Now we're gonna do something more interesting. Okay. So what is that thing? And this step gonna take just linear time still. Okay. So if this step takes linear time, this step takes linear time, this step takes ni times, just like yesterday. So the total running time is still fast, ni. Okay. But what is this thing? Okay. It's just gonna given any set t, and let's say the average of t is mu. Okay. I can return a and b. No, sorry. This is average of t on the projected position. Sorry. Okay. Let's say every node now is projected to the line, and every node has value. Sorry, this should be xv. Every node v has value xv, and let's say this is the average of the set t. Okay. Then what we can do is that we can return a and b and the threshold is eta, such that first of all eta separate a and b in the normal sense, this is the line, this is eta, and a is either a is here, b is here, or a is here, b is here. Okay. It's separate. This is what I mean. Okay. And I also have that a will be not too big, less than t over 8, and b is at least half. Okay.
Would the main difference be that now we're looking at the average of the projected points instead of the median, or
so we will look at the mean, okay. Yeah, the threshold here is not going to be the median, basically. But it might not be the mean exact. It might not be the mean too. This is just something that I will use in the proof. Yeah. But it will return some threshold. That is not quite a median. Okay. Now it's gonna have these two specific technical property that we will use, but the intuition is just that this threshold eta is not going to be too close to a, which kind of says that, which says this thing. You don't need to care about this so far. It's just some. Yeah, forget this for now. Yeah, but intuitive is that the eta is not too close to a. The intuition is that. For this one, the intuition is that a will contribute quite significantly to potential after projection. So after projection, this looks like the potential, right? The potential is just the distance from your position to the average square, summing over everything. That's the potential. But here is just the potential after projection. This is the projected position, this is the projected average, and this is distance square after projection. And this thing just says that the set A, if you just look at the potential that is contributed by the set A, this is quite big, not too small, constant factor. Okay. So let's see, let me try to tell you why this should be possible. Okay. How to return this thing. Okay. Okay. Good. If you look up the proof, it's just going to be a bunch of math, but the idea is just this. So, suppose first that imagine that the points are balanced in a sense that, let's say that this is there is a set of points here, and they are exactly have the same structure. Let's say they are symmetric. like have like a n t over 2 nodes here, t over 2 nodes here, and then this would be the mean. Okay, just at the middle is the mean. Okay, what would you do in this case? How would you choose eta in this case? Yeah,
We just choose the mean.
exactly. You can just choose the mean. It will separate. It will just separate A and B. Okay, and also this thing will be just satisfied. Okay, and what you do with A, you don't want A to be t over 2. You would just take like t over 8 that is furthest away. Why is that? Because like right now this thing kind of contribute half to the potential, right? When if the picture just looks like this, then you have that for all points in A. This thing minus mu is just like half. Let's call P to be P is just like the sum of this thing. P is just kind of the whole potential. Right now you have that this is just P over 2. Right? And if I take like the furthest 10 t over 8 guys, then this set, let me call this thing left part, and this is like this now is my A. Okay. This thing is just P over 2, but if you now sum over A, the same thing here, this is gonna be like P times 1/4, right? Because it's like the 1/4 fraction that contribute the most to the potential. So you're gonna certify this thing too. So if they are balanced, you can just return the mean and take the most deviate set here. But what will happen if you cannot return this? Let's like intuitively think what can happen if this is not true. If you take if you now let's say I claim this. I just draw it. If this is your mu, the mean, okay, and let's say the left part is less than half, the right part is more than half. Without loss of generality. Okay. And so this is like something in the left, something in the right. But when I take like, if I try to take like, actually let's say that, but suppose that the left part contribute to the potential like so tiny. How can that happen? Do you see like what would be your suggestion? Like how can the part on the left contribute to the potential so small? What need to happen on the right?
The points on the right side have to be far away compared to the left.
Exactly. There must be some guy on the right
which is fucked.
That is so far away. So like when it contribute, like the potential is like a square, right? So if there are like maybe some one guy here that is like really far away, then it contributes to the potential so much. But at the same time, the right needs to be quite big. It's more than half. It's more than half. So there must be a bunch of guys that are like kind of close to mean, and there's like tiny few nodes that are like really far away. So if this happens, what would you do? Well, just choose eta to be something like this. Then like just kind of shift eta a bit to this part. That you kind of know that now I shift eta to here, and now I claim that this is my B. B will contain like more than half of nodes now because a large number of nodes is here. This part now is going to be small. But it's still going to contribute a lot to the potential. And for the third property, you're going to have that too because you're going to shift eta to this side just by something tiny. So the distance from everything in A here to eta is basically not much smaller when you compare A to mu, which is just to say this thing. The distance from everything in A to eta is not so smaller compared to the one to mu. Okay? And if you scribe this, you might want to add a calculation, but this is like the picture. How do calculation work? I put it here. So, but you can look at this paper. Okay. But anyway, we're gonna get this set. Okay. Okay. So now let's analyze it. Analyze everything again. So the claim is that after a few rounds, then the potential is small. If we can do this, then we're done. And we're gonna use two lemma that we discussed yesterday. The first is that when you have a matching edge, that matching edge will, after like you average the 2 points, it reduces the potential by basically distance of the two endpoints square. Okay. And another key lemma is just this thing where intuitively we just say that the distance square between any points after projection are basically preserved. Okay. It can deviate by like after scaling by n. Yeah. Okay. Okay. This is a distance from between A and B before projection and after projection. Distance between A and the average before projection and after projection. They are basically the same after scaling by n. Okay. So now now we are ready to analyze it, to analyze everything. Okay, so what we're gonna do is we're gonna analyze how potential decrease per round, and the goal is the same, which is we're gonna say that the potential after I is something like this thing over log n. If we can do this, we are done. Right? That's kind of the goal. If this is true, then repeat this log square rounds, then you're done. Okay, but now I just gonna be a bit more fine-grained. I'm just gonna break down to this one minus. This is the potential like at the end of I plus I-1 round I-1, which is basically the same as potential at the beginning of round I. And then this is at the end, this is just the potential at the end of round I. So now let me break it down to like several steps. So imagine that this thing is just the potential after I update the position of points by the matching. So for each matching, I just take the average. That's how I move points, right? So the only thing that changed is the position of points. I change from this to this thing. I don't delete anything yet at this point. Just update the position. This is like a next step where after updating the position, now I delete the points in D. So now I update the active set from the previous one to the new active set. But so now I both match and delete. But this is not quite the new potential yet. The new potential is actually the same thing, the new set, the new position, but it needs to take the new average too. Okay, so that's how things really change. I kind of break down to update the position, update the active set, then update the average point. Okay. So now, yeah. Should I just, yeah. Let's see. I should finish actually. Good. So this part, how much the potential change after I match. It's just exactly like for each matching, the distance between the two endpoint square. Okay, that's how things change here. How about how things change here? This is the part where I just delete the set. So I just sum over the thing that I delete and the term in the potential of the which is just the distance from itself, from the node U to the average. That's how much thing decrease here when I delete. Okay. How about this one? This one is just how much the potential change after I move the average. Okay. But I claim that this this is at least 0. That is, this thing is at most this thing. Why do you think so? Do you see this? Why this one must be smaller than this one? Yeah.
Would it be because after deleting, the average can only go down, after?
Because it is the average, I guess.
Yeah. So the average might not go down. Like the average is kind of points in the space. It's not clear where it go down. But the reason is is that this is the definition of average. Average is the point such that you minimize